on mute. Oh, couldn't believe it.
Do we need laptops?
No, I don't think so, because it's going to be a lot of blabbing. So, yeah. Yeah. I've got it just in case, but I think I'm just going to steal the output that we might be looking at, because I just want to talk about it for today. We'll get this set up here. It's 240. Okay. And I'm so thrilled because I managed to hunt down a test bank, which actually has theory questions. So, but I need help from the Moodle people to help me get it into Moodle. But I looked at the questions and I think the questions are actually pretty good. They're exactly what I would have wanted to make anyways. And so, so once I get that set up, I'll put a couple of Moodle questions on there. And then it'll be less making output, more interpreting output. It's like we wanted it for the class assignments, right? Still making output for the labs, but I'm so thrilled because it's exactly what I wanted to do. And now I can hopefully do it. So stay tuned. I just found it last night. And I was like, oh, it's here. Okay. Okay, just Emily, be cool, be cool. All right. We're going to try to get through chapter 3 today. Just building on last day, right? Multiple regression. And so we talked about, just as a quick review, oops, I like this one instead. As a quick review, we talked about multiple regression. And we said, okay, well, now we're just allowing for more than one predictor, right? And so it allows for more than one predictor. Right? In fact, it allows for x1, x2, all the way up to xk. Which means we have k predictors. Oops. Sorry. My handwriting is not good, but it's not good. Even if you look at these notes, it's not good. So there's no excuse, but sometimes I let it get a little bit out of hand. So try to rein it in. Like, do you know what the problem is? When I was younger, we had to handwrite everything. And so like my default is handwriting, but kids these days can't read handwriting. And so for some reason, they just don't get it. So I have to print everything now. Weird, right? Should just be handwriting everything. There it is. So we're allowing for more than one predictor. And so we said, not all predictors have to be numerical, right? We don't have to have just quantitative predictors. In fact, we can allow for categorical predictors. And for now, we just talked about the indicator variable, right? So we talked about the indicator variable, right? Which is just often it's called a dummy variable, which I'm not sure I told you guys, but I'll throw it in the review as if I told you. Remember this? I feel like my props used to do that all the time. Oh, you remember this from last day, right? No, it's nowhere in here. So a dummy variable, right, is just a 0, 1 indicator. I don't know how else to say it, right? So is when we using 0 or 1 as the indicator. Right.
Is that the same as the sex?
That's right. Yeah, so when we use the sex variable, we coded it as 0, 1s to make it an indicator, right? And so we said, okay, well, coding sex, for example, as 0 or 1 makes it an indicator. We said it didn't really matter which one we use. In fact, and then I don't know about you guys, but I played around a little bit in R and just to see how it would behave if I just gave it a categorical variable with only 2 outcomes, right? So I gave it just the sex and it was able to handle that. And so it would just tell me which one is the indicator. So which one is the 1, right? And which one is the 0 is the other one, right? And so essentially the 1 turns it on, right? So turns that slope on, and then the 0 turns it off again. Right? So we talked about, okay, well, y hat is beta naught plus beta 1 x1 plus beta 2 x2, right? Where x2 is an indicator. And we said, well, no, I'm going to clean that up. Right, we can turn beta 2 on or off with that indicator variable. And it's going to affect your intercept. So the indicator affects the intercept. Right, and it allows for 2 different intercepts. Or multiple intercepts, right? If we extend it past an indicator, but we're just focusing on an indicator for now, right? Whereas then we said, okay, well, what if I want to look at an interaction term, right? So we talked about interaction terms. Interaction term is x1 times x2, right? That's an interaction term. And so now our model looks like y hat beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2. So now this is going to allow for a different slope depending on if x2 is turned on or off, right? And a different intercept. And so this allows for different slopes for each grouping variable, I'll say. For each grouping variable. And what we said is in R, right? We're just going to feed it how we want these predictors in there, right? If we want x1, x2, or plus x2 plus x1 times x2, we can just plug those in the way they are into our linear model in R, right? And so what I'm going to be doing for the next, because we're going to be talking about more models today, I'm just going to give you the general model. And then from there, we'll be able to see that, okay, well, if I just plug those in the way they're presented in the model, right, that's how I'm going to do it in R. So any questions about the review? Oh. Okay. So I had to cheat. It was too much to remember in my head. I was pretty proud of myself for having had everything in my head so far. So it's pretty good. Now I've got little notes here. So now I can tell you that we're in section 3.4, stuff like that. So section 3.4 is called new predictors from old. Oops. From old predictors. So what we're going to do is we're going to go back to just a single predictor to start, right? And then we'll work our way up to, but just to two predictors, right? Because sometimes we can have just two predictors, two really good predictors, and we can manipulate them in different ways to get just a kind of a bigger model from these two predictors, right? So we don't have to have a ton of predictors. And we talked about this last day too, right? That we don't want to overfit our model, right? We don't want to have too many things in there because our R squared is always going to increase the more things we have in there. So it's always going to be a better model, right? But we don't want to have an overly complicated model, right? And so now we're going to start, go back to just one predictor, right? And manipulate it a little bit to make two predictors. So we already saw the indicator, right? Or sorry, the interaction term, which I should put in here. No, we already said interaction term. For some reason, that's the word that I keep forgetting, interaction. Indicator is fine, interaction, keep drawing a blank. Anyways, so an interaction term, right, we've already seen. The interaction should be multiplying, bless you, should be multiplying, but I'm sure you could, because that's multiplying by the inverse, right? And so, sure, you could probably put it like 1 over x2, is that what you mean? So multiply x1 by 1 over x2. Sure, might be worth a shot sometimes. I'm trying to think what x2 would have to look like to take 1 over x2.
But your x2 is just 0 or 1, right? I mean, this formula would only work if x2 is 0 or 1.
Well, today we'll talk about, so what I was just about to introduce actually was x2 does not necessarily have to be an indicator variable. It's easier to think about if it's an indicator variable, right? Because it either turns it on or turns it off, right? But what we can actually have is we can actually have just a numerical variable, so a quantitative variable. But just like how the indicator allowed for different slopes for each of the groups, right? If we have 2 groups, that's fine. If we're talking about a numerical variable, it's allowing for a different slope at every value in that numerical variable, right? So it's a little bit harder to wrap our heads around, or at least for me, right? It's harder for me to wrap my head around it because then the slope is like moving incrementally. But let's start there. So we can have an interaction term with 2 numerical variables. Do you guys prefer numerical or quantitative? I forgot, I think I asked, but I can't remember what. Maybe nobody cares. You guys are flexible. Yeah. How about that? Often when I write quantitative, I lose track of how many T's there are. Quantitative. Yeah. So with two numerical, so we can have an interaction term with two numerical or quantitative variables. That is to say that x2 does not need to be an indicator. Or even categorical, right? It doesn't need to be categorical even. Slash qualitative. Qualitative. But in the model, right, y hat is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2. Right. Now, this interaction term allows the slope to change for every value. So it allows the slope to change for one predictor. Sorry, I had it written out here and I bungled it. It allows the slope with respect to, that's what I bungled. Allows the slope with respect to one predictor. Change for values of the other predictor. That's what I wanted to say. I was trying to think of a way to paraphrase, but with respect to one predictor, change for values of the other predictor. So now we're talking just predictors in general, it doesn't matter, right? And so the slope of one of the things is going to change with respect to the other predictor. We can simplify our model, right? If we just bring it back down to just one predictor, right? But then we can kind of kick it up a notch because sometimes there is just maybe one predictor that we have, but we need to get a better model, right? So sometimes there is only one predictor of interest. We'll just call it X. That we want to use to make a more sophisticated model. That we want to use to make a more sophisticated model. We can start with a quadratic regression equation. Remember, a quadratic is just ax squared plus bx plus c, right, in regular math? That's a quadratic. And so now we've got x squared, oops, plus bx, or ax squared plus bx plus c, right? We can use the quadratic formula, blah, 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 go off on a tangent, right? But I only bring this up because we know what the quadratic formula looks like, or the quadratic equation rather looks like. And so it's not going to be that big of a stretch to say that the quadratic regression equation is going to look something like y is beta naught plus beta 1x plus beta 2x squared. So now I've got this squared value of x in there. But we've got the same x in both of these, right? But I'm getting two coefficients, right? Beta 1 and beta 2. I want to go and steal from the textbook a little bit. I really hope I marked it off. I did. So here, right, if we've got a relationship that looks like this, right? So we've got this curvature, then I want you to think of a parabola, right? X squared. And so then you're going to say, okay, well, what if I try to fit a quadratic model to this, right? Because I want to capture that U shape, right? So now we're not forcing it to be linear anymore. Now we're saying, well, actually, we can draw different types of lines, right? Knowing what x squared looks like, this looks like x squared, right? And so I'm going to fit a quadratic equation. And so we get this. Oops. And it doesn't really matter what it's about because I just wanted to show you what it looks like. Or actually, maybe I can fit it on the same page. I cannot. Maybe I can. How about over there? Right, and so now we've fit this quadratic model, and it actually looks like it's doing a pretty good job, right? And so now we just needed, so it's measuring the CO2 levels for each day of the year after day something 91 or something like that. So like I said, it's not important, but the CO2 levels decrease as we get into summer, and then they increase again as we get out of summer. And so apparently that's what the graph is telling me. I don't know these things. So if we had to model this, I'm going to think, okay, well, could probably do a quadratic here, right, to try to capture it. This one has kind of a cool example about, because we might be concerned about this little outlier up here, or even this one, right? But mostly this one, because it's a little bit way off, right? And so here's one of those examples where this is an outlier. But if we remove it, it actually doesn't change anything. And so we've got the blah, 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 blah here. Stealing this. Oh. Just so we can see it. So the solid line is the original, right? And then the dotted line is the one with the outlier removed. I'm okay with that, right? I would probably just keep all the outliers, right? Because the original model is actually capturing a lot of that stuff. It's not being pulled towards the outlier. So this is one of those instances where, yeah, you could probably take it out, but there's no reason to, because you get basically the same model, right? And so it's capturing a lot of that activity.
So will there be any instances where removing outliers will show an effect on your prediction or your model?
Yeah, so that's the thing with outliers is we remove them. We look at our R-squared, right? And we look at just the plot, right? What does it look like? Does the line, do the coefficients change a lot, right? Or do the coefficients change significantly, right? And so in this case, it didn't change, right? And so I would probably keep the outlier in there. But in terms of dealing with outliers, you remove it. If you have more than one, right, you remove it, you put it back in, remove the other one, put it back in, remove two, put them back in, remove another two, right? And so if you've got little clusters of outliers, right, you can remove them all, see what happens. Just always keeping in mind that you want to keep as much data as you can. And then just see which one gets you a better model, right? Because, for example, if this new model, right, if the old model was just kind of like kind of a shallow dish here, because it was trying to capture this one, then I would say that this dotted line with the outlier removed would be a lot better, right? That would be a better model because it's actually in the center of all these guys. And we've got relatively even spread around the line all the way across. Whereas if the original model had been up here, right, that doesn't look so good because it's trying to capture this little guy up here, right? So if we had a bad model fit, let's see if I can find a different color here, maybe green or red because it's bad. This would be a bad model fit, right? If we removed the outlier and it dropped us down to what we're looking at in the actual model, right? Then yeah, I would say you have to remove that outlier because you're sacrificing one to model many, right? Here, you're sacrificing modeling many for just the one data point, and so you have to have that trade-off. But usually it just comes down to arguing it. Just do whatever you want. Just argue it.
Just make sure you're putting all those points nearby to that line. That's it.
Yeah, pretty much. And this is the good model. Oh yeah, nice. It might be tempting to go for a polynomial, right? So more than just the quadratic, right? Cubic, quartic. What's 5? Pentic?
Poly is.
Let's just say poly. Poly is just many, right? So let's just say polynomial. X is 6. Septa, octa. Say that again.
Trigonometric functions to use the trigonometry and sine cos.
Yeah. But if you've got that kind of cyclical relationship, that if you're trying to model something cyclical, it's very likely that you have some sort of time series going on in the background. And so, which is another, well, it's a way here in the back. I think it's chapter 12. So it's got its own thing. It is, yeah. So we do need to take that into account. Here we've simplified it a little bit, right? We're ignoring the fact that it's a time series, but we should be aware of it. We're not going to get to time series. Time series is like its own field, basically. So, so we're not going to get there. But if you're interested, it's at the end of the book. Yeah. And so, hey, no problem. Yeah, so it is a time series. We do need to be aware of that. But for this course, we're just going to kind of ignore it, right? We're just going to model it as if it's fine. And then if you have to later on look into time series, the stretch isn't going to be that big, right? It's just taking into account the relationship between the previous observations. Okay, what did we want to say? Oh yeah, we could stretch it for, we could make a polynomial model. A polynomial model, y equals beta naught plus beta 1x plus beta 2x squared plus all the way up to beta k x to the power of k. Notice that these are all the same x, right? So they're all just one explanatory variable happening again and just being powered. That might look like a fancy model, but often anything past the x squared isn't going to help that much. And so these terms usually won't help improve the model. Significantly. Right. So usually a quadratic is good enough. It's kind of sophisticated enough. Notice that it captures that kind of the parabola shape, right? And so that's good. And it's nice to be able to think about just one explanatory variable, right? One predictor. And so sometimes a quadratic's all you need, right? Another type of model is just an extension of the quadratic, but it handles two different predictors. And so that's the complete second order model. And so a complete second order model has two predictors. X1 and X2. So now we're back into multiple predictors, right? But we're just tapping out at X1 and X2 for now. You'll see why, because a complete second order model, what happened? It's okay. Is y is beta naught plus beta 1 x1 plus beta 2 x2. So they each get that linear slope, right? Beta 1 x1, beta 2 x2, and then they each get their squared, right? Beta 3 x1 squared plus beta 4 x2 squared. And we get the interaction term in there for the two of them, right? Which also has its own slope. So we get beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 squared plus beta 4 x2 squared plus beta 5 x1 times x2. So here, we call these the linear slopes. right? Or the linear predictors. Kind of focusing on just the squareds, right? The squares make it the quadratic. And then we've also got the interaction in there. So a complete second order model, second order meaning we've just got the two predictors, right? X1, X2. And so now I have to create, okay, I have to have X1, X2 on their own, and then I have to have X1 squared and X2 squared, and then I also have to have the interaction between the two. This is a huge model, right? I've got so many predictors in there, right? Variations on the same two predictors, right? And so usually we wouldn't go beyond this. You can have a complete third order, right? But then you would have to have each of the three individually, each of the three squared, and then each of the pairwise interactions, right? And so it gets huge right away.
Why not b to the 6 x1 squared x2?
Beta 6 x1 squared x2 squared. Oh, good question. I don't know. Just isn't. Yeah, so why wouldn't you have an interaction between the squares? It's too much. I don't see why you couldn't though. But the interaction might behave the same way. Right, it would just be a power of the original interaction.
Yeah,
but arguably so is x1 squared and x2 squared.
Yeah, but I'm thinking that b5 would be a9.
Yeah.
And x1 squared times x2 squared would be a.
Yep. I think the reason it's not in there is because we've already got the parabola with x1 squared and x2 squared. And so x to the, like some x to the fourth. I don't know. Because the interaction term is what lets us have a different slope for each thing, right? So I don't know. I'm gonna have to look into that and see why, because there must be some explanation that I don't know why we wouldn't interact x1 squared and x2 squared.
Or is it
something worth Googling?
Well, probably if it's a 0 or 1 indicator, then probably we just add another.
Yeah.
Intersect.
Yeah.
So, if it's both numerical, then it's totally U9 and U curve.
Yeah. Yeah, I don't know. It's a really good question though. Yeah, I'll have to Google it. Emily, Google. Oops, can't even write Google. X1 squared times x2 squared interaction. Why not? Why or why not? Maybe we do want to do it, but maybe because we're just starting in multiples, maybe it's too much. Note to myself in there. I'll have to remember to go back and look through my notes, which I never do. But I am curious because it's a really good question. Okay, we can make complete multiple order models, right? So we can create complete multiple order models, right? We just looked at the second order one, which means more than 2 predictors. But, and I'm going to put this on the same page here. But we need to include all of the linear, but we need to include all the linear terms, quadratic terms, as well as all of the pairwise interactions. All of the pairwise interactions. Oops. In general, if we've got these more kind of, let's call them sophisticated models with interactions or quadratics in there, we should also keep the linear predictors in there, right? The more basic predictors. And so we don't want to build a model with just the interaction. In fact, I tried in R and it actually doesn't let you, it forces in the individual predictors as well. And so, and that's just a rule of thumb, right? If we're making something with the quadratics, right? So with the squareds, we don't want to have just squared values in there. We want to have just the linear predictors and the quadratic predictors as well. So in general, we want to include the, I'm going to put it in kind of air quotes, the simpler terms along with our more complicated terms. So I'm thinking complicated in the sense of interaction terms or squared terms. So in general, we want to include the simpler terms along with our more complicated terms. I'll start that over. Complicated terms. Right, so things like x squared or x1 times x2. Those that I'm considering those your more complicated terms, right? When we move away from just simple linear regression or just kind of two-term multiple regression in our model. Even if they're not necessarily helping the model, right? So even if they're not necessarily significant in the model, which is a little bit backwards, right? Even if they are not significant in the model, right? We want to have those simpler ones in there. So it's possible, because that's as kind of high order as we'll go for our models for right now, right? But notice that they only really use one or just two predictors, right? So we can build lots of models even if we only have one or two predictors, right? We can extend them, make quadratic models, we can make complete second order models, even just the interaction term, right, gives us something to play with sometimes, depending on the relationship. And so in the next section, we're going to talk about if our predictors are correlated, right? So if our predictors have some relationship, which happens all the time, right? If we're saying, okay, well, X1 is helping me predict my Y, right? But so is X2. It's not unreasonable to think that X1 and X2 play off of each other as well, right? They're not going to come from two separate fields and be like, well, I affect Y, right? They're going to have some sort of relationship between the two as well. Right? That's not something that we necessarily need to avoid. It's just something that we need to be aware of. And so in section 3.5, and I'll try to be better in the future to just mention the sections that we're starting. I've been really bad about it, but now I'll buckle down and I'll try. We're going to talk about correlated predictors. And so correlated predictors, you can see if you make a scatter plot of all your predictors or all your potential predictors, you can see which ones are correlated, right? Because they'll have some sort of pattern in the scatter plot. You can check the actual correlations between two predictors, right? And so we call it multicollinearity. You know, correlated predictors is multicollinearity. Multicollinearity. Is when two or more predictors are highly correlated. Which can happen, right? It's not weird. And like I said, it's not something that we need to avoid, right? And so, which is kind of strange, right? Because it's going to affect our model, it's going to affect all our things, right? But just making a note here, we don't always need to avoid multicollinearity. But we do need to be aware of it. Because it could affect how we interpret the coefficients in our model. because it could affect how we interpret the coefficients in our model. The coefficients in our model. So remember how we interpret the coefficients in just a multiple regression, right? We said that the coefficient, right? So each of those slopes, let's call them, right? The coefficients, the t-test for each of them individually, right, was assuming that everything else is held constant. If two things are correlated, it's going to be really hard to hold one thing, right, and just look at the one thing as everything else is held constant, right, because we're saying, well, this one thing is going to move with another of the predictors in there, right? And so that's why we say, okay, well, we need to be aware that that could be happening. Sometimes it's fine, right? Sometimes that's what we need. And sometimes it's unavoidable, right? And so we need some way to be able to say, oh, I need to be a little bit more careful when I interpret these coefficients, right? Because the coefficient can't be held steady, or the other coefficients can't be held steady as I interpret this one predictor, right? And so here, let me see if I can find some output here. Where was it? I had one in mind. Let's just look at this little example for a bit. Just for a brief moment. Yeah. So here, what we're doing is we're trying to predict the price of a home using size in square feet, presumably, and number of bedrooms as the predictors. Is it reasonable to think that the size has nothing to do with the number of bedrooms, and vice versa, right? If you have a big home, it's more likely to have more bedrooms, right? If you have a small home, it's less likely to have a lot of bedrooms, right? And so they're going to move together, right? And so we say that the size and number of bedrooms are likely correlated, right? Which means that if I'm interpreting the slope, right, we said, well, for this kind of, I don't want to say simple, because simple means one predictor, right? But maybe context helps, right? So for this basic case, we'll call it simple probably, right? But for this kind of little itty-bitty example, right, now we've got an intercept find, we've got a coefficient for size and a coefficient for the beds. But remember that these coefficients assume that the other one is being held steady, right? But if I increase the size, then the number of bedrooms is likely going to increase as well. And so it's hard to hold that one down because it's going to move with the size, right? And vice versa. And so the coefficient here, let's see. the coefficient of size, which is the 31.169, tells us how much the price would increase, right, for each unit increase in size. Tells us the amount, the predicted price would increase for each unit increase in size. Right? Remember the definition of the slope, right? For each unit increase in X, we'll see a slope increase in the predicted value of Y. That's what we're saying here, right? So the coefficients behave the same way, but now that we've got more than one predictor, right, we have to tack on assuming that the other predictors and the coefficients stay the same. So assuming the other predictors are held steady. This is where I'll add in, right? This will be difficult, right? Because the size in the bedrooms are likely correlated. This will be difficult because the size and number of bedrooms is likely correlated. Right?
Where can you see on the statistic page to conclude
that they are correlated? We could look at the correlations, right? You could look at the scatter plot.
but not on this table.
Don't worry, there's a calculation that we can do. But before I get there, it's too fast.
Yep, I was just wondering because we are now saying that the size and the beds are correlated, but it's.
But how can, yeah, it's just based off of logic. So far, I'm just suspicious that that's the case, right? And so we can check. We can check if two predictors, right, or more, if two predictors, but you'll have to do them pairwise. So that's why I say two predictors. So we can check if two predictors are correlated. Are correlated using scatter plots, right? Looking for some sort of pattern, not necessarily linear, right? Any sort of pattern. Looking for a pattern. But also calculating the actual correlation. And there's the core command between two variables. And I think you can even get a correlation matrix where it just tells you the correlation between each of the predictors. Uh-oh. It's okay. It's okay. Looking for a pattern or calculating the actual correlations. And I'm pretty sure they did a correlation matrix here later on, blah, 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 blah. So here, write something like this. Put it in here. So you can look at the scatter plots. These are all the possible predictors. Actually. So if we're looking at the beds and the size, it does look like I have this pattern going on right between the beds and the size. Whenever we have a matrix, you only have to look at the one of the sections, right? One across the diagonal. And so I like the top, but maybe you like the bottom, I don't know. So the beds and the size, right? Even if it looks a little bit weird, we have to think about, okay, well, the size is on a continuous scale, right? Let's call it. The number of bedrooms, probably 1, 2, 3, 4, 5 bedrooms, right? And so it's going to be discrete, and so it's okay to have this kind of step, this ladder action here, because in general we would describe this as a pretty strong pattern. And so here, right, looking at this one, kind of trying to. As long as it's linear, it's okay. Yeah. Because you won't have half a bedroom, for example, and that's okay. It just doesn't take on those values. But as long as it follows this linear pattern, so it's not looking like, whoa, right? So you just kind of have to fill in the rest between there and convince yourself that it's linear, and then it's fine. Right, and so here, say that again. No, never, I'll never tell. So here, right, we've got this pattern. Oh.
Just curious, if you put a line between those two,
Mm-hmm.
It's not a good prediction as well.
Do you mean like if we fit a line here?
Yes.
No, because we would be able to get, if we're using the beds as the response, we would be able to say, oh, I predict that this house is going to have 1.45 bedrooms. That's still our prediction, but we would have to say something like, well, that's not going to happen, so then we have to choose between 1 or 2, and then we have to go back and look at our data and just kind of go from there. So it does involve a little bit more, but that's still our prediction, right? Somewhere in between there. It's just not something that you bring to your boss. Oh, it's easy. It's just going to have 1.45 bedrooms. Your boss is like, okay, thanks. So yeah. So then you have to decide, well, do I want to over-predict or under-predict? But yeah, so we've got this pattern here, which tells me that they're going to be correlated. Which is fine. That's what we suspected all along, right? We said, oh, that's reasonable to think. And so if we go in here and we look at, where's that?
Before that.
Was it the correlation?
Before the graph.
Was it before the graph? Yes. Thank you. Oh, haha. Thank you. Right before it. Right in front of me. It's always where it is. Right. So we can make something like a correlation matrix here. there's kind of varying degrees of correlations here. Again, we've got this matrix, and so just along the diagonal, of course, the correlation is going to be 1 because it's on itself. But if we look at the size and the beds, our correlation is 0.746, which is quite high, right? And so I'm not really too concerned about something like 0.356. 0.558 might be a little bit much, but that's against price, right? So might be a good predictor for price, right? Because they're so correlated. The lot actually has nothing to do with it. It seems got this negative correlation, very small. It doesn't matter, right? And so here, you kind of use your own judgment and say, yeah, that's pretty big, right? Or yeah, that's pretty small. For me, I just use a cutoff of 0.5 or a rough cutoff of 0.5. Should probably boost it out to 0.6 for being considered kind of strong, but I just like having that 0.5 cutoff, right? Plus minus 0.5 for going from a weak correlation to a strong correlation. So, okay. So knowing this, right, then we can say, well, right, those coefficients, they're fine, they're for our model, right? But in terms of interpreting them individually, they might not be that useful, right? Because the size, or sorry, yeah, the size and the number of bedrooms is going to move together, and so there's no way that I can hold one steady. Okay. How we quantify it, right, is through the VIF, the variance inflation factor, and so the variance inflation factor, oops, it's the VIF, and it reflects the association between a predictor and all other predictors, right? Between a predictor and all other predictors. So what it looks like is we can calculate the VIF subscript I, because there's going to be one for each predictor. So I'll put that in here. One for each predictor. Is just 1 over 1 minus Ri squared, where Ri squared is from a model predicting Xi using the other predictors, right? So now we're completely ignoring the response variable, and now I'm just saying, well, how well can I predict size from the number of bedrooms, right? And then I get an R squared from that model, and that's the R squared that goes in there. This is not something that I would get you to do by hand, right? I just want you to see where it's coming from. And so, because it's a manageable equation, right? And so this is from a model predicting Xi using the other predictors, in the model. So it just pulls out each individual predictor, makes a new model with just the other predictors in it, calculates the r squared, and then does 1 over 1 minus that r squared for each of the values. And what you'll find, and I think we'll do this on Monday, because I'm feeling the crunch time here, is we can get the VIF tacked on to our output. Where is it? Here. Different data, but it's okay. So here, it's just calculated the VIF for each of these. Now we need to know, okay, well, what's good, what's bad, right? And so here, can add the VIF to our regression output. And we say there is multicollinearity. There is multicollinearity. Ugh. If the VIF is greater than 5. This is the same as saying that the R squared, Ri squared is more than 80%, right? So we're using an 80% cutoff, right? And so, which is really quite high, right? And so an R squared of 80% or more than 80% gives us a variance inflation factor greater than 5. So what we're looking for is just a kind of a chopping block here. Anything with more than 5, right, says that there's multicollinearity with the other predictors. Right? In this case, we're going back to the number of doctors to the hospitals and the number of beds in the hospitals. Doesn't really matter, you can talk about any predictors here, right? And so, but now what this is telling me, right, it's what we were talking about earlier, is that these coefficients, yeah, they're for our model, we need them, right? But as far as interpreting them individually, it's not gonna be as cut and dry, right? They're gonna depend on each other because there is multicollinearity.
So anything, or is there any added value on the numbers of the VIF? What I mean is that for as long as it is greater than 5, then you conclude multicollinearity, or let's say because one is 16, one is 14, one is 6. So
yeah, I think like these are all greater than 5, but this one, I mean, 6. So what would I say? Yeah, we could probably look at this coefficient, right, and just kind of say that, well, I could hold these two steady because they seem to be tacked onto each other, right? Which kind of makes sense, but in general, I'd be hesitant to interpret this coefficient on its own and not these ones, just for just consistency, I guess. Right? And so I would say that if there is one that's higher, right, even if the rest of them are 3 or whatever, right, I would still be cautious in interpreting the coefficients on their own. Does that make sense? Does that answer the question? I feel like it didn't, but I don't know what else to say. Because so, just so I get it straight, right? So you're saying, let's leave this 16 as it is, right? And let's make this one 2 and this one 1. Yeah. Is that the situation you're thinking of? Yeah. Okay. Then I would still say, no, we shouldn't be interpreting these like we would if there was no collinearity, or no multicollinearity. So I'd say any VIF that's high, right, means that we need to be extra cautious when we're actually interpreting these one by one. Okay. Pretty sure I'm out of time. So, any questions? No?
Probably more questions.
Yeah. So we've got our lab on Monday, so we won't see each other on Friday. We're not too sad about it. We've got extra time on Monday again, right? And so have a good weekend, I guess. Weird. Yeah. See you later.
You just need to submit one lab assignment.